welcome to solving basic IVPs with impulse forcing functions. So recall we defined essentially delta of t minus t naught to be the limit as h goes to 0 from the positive side of the function that's 0 for t less than t naught, 1 over h for t naught less than or equal to t less than t naught plus h, and then 0 for t greater than or equal to t naught plus h. And we saw that the Laplace transform of delta of t minus t naught was simply equal to e to the negative t naught times s. So now we are going to go ahead and look at some basic IVPs of the form a y double prime plus by prime plus cy is equal to delta of t minus t naught with the initial conditions y of 0 equals 0 and y prime of 0 equals 0. So if we set the Laplace transform of y of t to be equal to capital Y of s, with those 0 initial conditions, we wind up getting that the Laplace transform of y prime of t is simply equal to s, capital Y of s, and the Laplace transform of y double prime of t is equal to s squared, capital Y of s. Again, this is only because those initial conditions were both equal to 0. So plugging in, we wind up getting then that a times s squared capital Y of s plus b times s times capital Y of s plus c times capital Y of s is equal to the Laplace transform of delta of t minus 1, delta of t minus t naught, which is e to the negative t naught times s. So this is taking the Laplace transform of the equation. This winds up telling us that capital Y of s is e to the negative t naught s over as squared plus bs plus c. So if we set capital W of s to be equal to 1 over as squared plus bs plus c, in other words, 1 over the characteristic polynomial, then we have that capital Y of s is equal to e to the negative t naught s times capital W of s. And therefore, we get that y of t is the inverse Laplace transform of that, which is just u of t minus t naught times w of t minus t naught, where w of t is the inverse Laplace transform of capital W of s. So we can solve these IVPs simply by figuring out the inverse Laplace transform of 1 over our characteristic polynomial, and then multiplying by our step function with our translations. So if I should note that this is taking the inverse Laplace transform, how we got from capital Y to lowercase y. So let's go ahead and solve the IVP y double prime plus 6y prime plus 10y equals delta of t minus 5 with initial conditions y of 0 equals 0 and y prime of 0 equals 0. So in this case, our T naught is 5. And our characteristic polynomial is s squared plus 6s plus 10. So if we set capital W of s to be 1 over s squared plus 6s plus 10, otherwise known as 1 over, we have s plus 3 squared would give us s squared plus 6x plus 9, and then plus a 1 squared. This is precisely the Laplace transform of e to the negative 3t times sine of t. Right? That goes to omega over s minus lambda squared plus omega squared. So we get that our w of t is that e to the negative 3t sine of t. So our w of t minus t naught, we're looking at w of t minus 5. So that is e to the negative 3 times in parentheses t minus 5. And then that's multiplying sine of t minus 5. And so our final solution, we have y of t should be equal to u of t minus t naught. So u of t minus 5 times w of t minus 5. And we wind up getting that y of t is u of t minus 5 times e to the negative 3 times t minus 5 times sine of t minus 5. So this is our solution to the IVP, where we didn't have to do quite all of the work that we're used to doing because we do have this generic form to solve. In the next video, we will look at slightly more generalized IVPs where our initial conditions are non-trivial. And we will also incorporate a component of our forcing function, which is not an impulse function.